This is lesson 7.1 for Secondary 2 Honors Math. It is about quadratic inequalities. It's kind of a carryover from our last unit. Just put it in with this unit 7 because it's kind of short anyway. So to review what we already know about inequalities, what you've done in the past to solve an inequality, like what we see here, you have 2x and you're going to add 4 to both sides, and so x is greater than 7/2. And so you put that on a number line, so 7/2 is 3.5, so we can put it in between 3 and 4. And then you have an open dot, and it's going to be greater than, so it goes that direction. And so the graph shows us where all of our solutions are. So all the numbers that are this way are all solutions and will all be true. And then we can write that in set notation as x such that x is greater than 7/2. So we want to stick to fractions as much as we can. So number 2, because I have x on both sides, one thing you're not going to do is do not divide by x. Okay, you cannot do that because x might be 0, and that's going to make you divide by 0. So you cannot do that. What you're going to do is you're going to get all the x's on one side. So I'm going to subtract 10x. So I'm going to have 3x take away 10x is greater or less than 0. So negative 7x is less than 0. So now I'm going to divide both sides by negative 7. Now remember that when you're dealing with inequalities, when you divide both sides by negative, you have to flip the sign. So if you don't flip the sign, you're going to get the wrong answer here. So it's going to be greater than 0. So that means that all the numbers that are greater than 0 will make this a true statement. So we can try something like 1. So 3 is less than 10. That's true. So anyway, if you did not flip your sign, you'd be saying all the numbers less than 0 were going to make this true, which you can try that and see that that's not going to work. So anyway, that's how we solve inequalities that we've had before. Now down below it says give 4 solutions. So just give me 4 numbers that would be solutions. So for number 1, numbers like 4 would be a solution, 16.8 would be a solution, 217 would be a solution, I don't know, 11/2 would be a solution. So those are just 4 examples of solutions. Over here, 4 solutions here, it could be like 0.7, 1.8, 20, or 14. Okay, so those are all solutions. So just getting the idea of that whole interval is going to be full of solutions. So we have a lot of solutions. Okay, so in numbers 3 and 4, we're going to go back and remember how we graphed linear inequalities when we did this. So we did this last year, and so when we have something like number 3, you're going to start with your y-intercept being at 4. You have a slope of negative 2. And then remember, when we graph these inequalities, we look at the inequality symbol, and if it's greater than or less than, we're going to do a dashed line. Now, because it's an inequality, it's greater than or less than, and so all of our answers are either above the line or below the line, and so that's where we're going to shade, because it says greater than, so we're going to shade above the line. So what that means is it means all of the points that are in this purple region, they're all solutions. So just like when we had on the previous page, like all of these are solutions, they're all in this shaded part, and it's the same thing we're seeing here. Everything in that purple shaded region is all a solution. Keep in mind that the numbers right on the line, because it's a dashed line, are not actually solutions. That's a borderline. So then to do the next one, number 4, first I'm going to divide everything by 2, and so make sure you get everything divided by 2. So you're going to have y is less than or equal to negative 3x plus 1. So I'm going to graph that. So negative 3x, I'm going to go down 3 and over 1, get my slope. Now because this is a less than or equal to, I'm going to have a solid line when I go to graph my line. It's still an inequality though, so I have to shade either above the line or below the line. Since it's less than, it's going to be below the line, and so all of those are my solutions. Now if I said give me 4 examples of solutions, because we've got both x and y, it'd have to be an ordered pair. So I could say something like negative 3, negative 1. That would be a solution. Negative 5, positive 4. That would be a solution. So on these, we only had 1 variable, and so it was one-dimensional, basically. And then on this one, because we have 2 variables, we have to say the solutions differently. So in the 1 variable, we could write set notation. We also had a way to represent it on a number line, but in this, when we have 2 variables, we have to represent our solutions by graphing, and so that's something different. When you do state a solution, it's going to be an ordered pair because you have those 2. So when solving a quadratic inequality, so going from linear to quadratic, if you only have 1 variable, like what we saw on 1 and 2 with the linear inequality. If you only have one variable, you're going to show your answers by showing your intervals on a graph. Okay, so quadratic inequality with one variable, you would still use a number line for your graph, and you would show the interval just like we did up here, but you're going to have more than one interval a lot of times. Not all the time, but you're going to have maybe from here to here and then from another place. But you would also be able to write set notation, and that's really the best way to write your solution if you can. So if you only have one variable, set notation is the way to go with that. So you're going to use what you know already about quadratics to find the intercepts. So where does this quadratic, where does it cross the x-axis? Because those are my solutions. Okay, remember that the intercepts are dividing lines or dividing points between things that are above 0 or positive and below 0 or negative. So remember that when we talked about quadratics and we talked about, if we have a graph, you have a positive part of your graph and then you have negative parts of your graph. When we talk about quadratic inequalities, we're talking about all the things above or all the things below. So we'll see that when we get into this. So the next set of examples we're going to do is we're going to solve quadratic inequalities. Notice that they only have one variable. So this is still along the lines of something like numbers 1 and 2 that we saw at the beginning of the lesson. So we're going to solve this similarly to how we did in 1 and 2, but it's a quadratic, so we have to go about it differently. So remember that if you have something like you see in number 5, you could use the quadratic formula, but you can only do that if it's equal to 0, and so that only gives us an idea of where the dividing point is. You'd have to test points to see if it was greater than or less than. Because quadratic equation, to solve that, you have to have it equal to 0. Same with factoring. If you have factoring, you have the zero product property. That works if it's equal to 0, but we have greater than or equal to 0. So you can't say anything greater than or equal to 0, because how do you get numbers? If you multiply two numbers together, how do you get something that's greater than or equal to 0? Well, to get equal to 0, one of them has to be 0, but what about greater than? They could both be positive numbers or they could both be negative numbers, and so that's why it doesn't work to just replace the equal sign with a greater than or equal to. So we're going to have to try a little something different here. We can use factoring to help us find the points that we're interested in, and so I'm going to factor this. And so what I've got is I've got that x minus 5 and x plus 3 is greater than or equal to 0. Now here again, that doesn't tell me that it's going to be numbers greater than 0. It tells me that those are my dividing points. So remember when we had a quadratic and we have from here to here, let's see, that's negative, and then from here to here is positive, and then from here to here is negative again. That's kind of what we're talking about. We're talking about dividing points. So on a number line, again, just because we only have one variable, we're going to use a number line. So let's put positive 5 there, and we're going to put negative 3 there. Okay, it doesn't really matter so much how far apart they are, just label it. Okay, so basically I've divided my number line into 3 sections. What I need to do now is I need to test and see where are my solutions, find them. So pick a number that's in this section. So something like negative 4, negative 10, negative 3,000. I don't care, pick something kind of easy. So I'm just going to choose negative 5. So what I'm going to do is I'm going to plug in negative 5 into the original equation. So negative 5 squared minus 2 times negative 5 minus 15, and I'm going to see if it's true. Is it really greater than or equal to 0? So that's 25 plus 10 minus 15. That's 25 plus 10 is 35, minus 15 is 20. Is that greater than or equal to 0? That is greater than or equal to 0. And so what I like to do is I put a little happy face because that was true. Okay, now I go to the next section, and I'm going to check a point in there. So between negative 3 and positive 5, an easy point to check would be 0. So I'm going to try that one. So 0 squared minus 2 times 0 minus 15. That's 0 minus 15 is negative 15 greater than or equal to 0. That's a no. So I'm going to put a little sad face there. Okay, and then I have one more interval to check. So I'm going to check the next one. And so something bigger than 5. Don't pick 5, something bigger. So like 6 or 10. So I'll use 10. So I can do 10 squared minus 2 times 10 minus 15. So that's 100 minus 20 minus 15. Is that greater than or equal to 0? That is. So I put a little happy face there. So what I see is that I have two intervals of my number line that are my solutions. My solutions for this inequality are located there and there. And so when I go to write this in set notation, I'm kind of squished up there, so I'm going to write it down here. I'm going to write x such that, and we're going to say x is less than or equal to negative 3, or, okay, now we come back to the meaning of the word or. It's not going to be negative 3 or less than negative 3 and greater than 5, because tell me a number that's both of those. There's no such thing. Or it can be x is greater than or equal to 5. So if I have a number in this interval, or if I have a number in this interval, they are solutions. And so this is how I would write that in set notation. So really I'm using the number line as a tool to help me find my solutions, but I'm going to write my solutions in set notation. So going to number 6, let's try that one. This one is the same quadratic part, but this time it's going to be less than or equal to 0. So I know that when I factor it, I'm going to have the same factoring happen. But this time I'm looking for less than or equal to 0. I'm going to have the same dividing point, so negative 3 and positive 5. I'm still going to get this in 3 sections. Now, since I've already done the testing, I know like what's happening. This time, since I want it to be less than 0, where is it less than 0? It was right in here. Last time it was a frowny face because I wanted it to be greater than 0, but now it's a happy face because I wanted it to be less than. So by the same token, those intervals do not work. So where are my solutions? My solutions this time are between negative 3 and 5. If it's between, the numbers in there are less than 5 and at the same time they're greater than negative 3. So actually you can write this as a compound, and we talked a little bit about this last year, a compound inequality where you have x is less than or equal to 5 and at the same time greater than or equal to negative 3. Okay? People always ask, like on this one, on number 5, they always say, could I write like this, like greater than 5 and then less than negative 3? You cannot, because logically, what does that say? It says x is greater than 5 and at the same time it's less than negative 3. So logically that doesn't make any sense. So no, you cannot say that. The only time you can do a compound situation like what we see here is if you've got something in between 2 points. Okay, so let's do a couple more to practice. So if you want to pause on number 7 and 8, I will tell you that you are going to have to move that number to the other side because you do have to get 0 on the one side. Just like when we're solving equations, you have to get 0. And so you're going to do the same thing with inequalities. You're going to find the points that you're going to put on your number line, and you're going to have to do test. And so pause the video and let's just see how you do. Okay, for number 7, this is what you should have had as far as moving everything around and factoring. So 2 and 6 are my 2 points that I'm going to change. So I have to test something here, here, and here. So that's where I have to go and test things. And so I'm just going to start picking numbers. So just make sure you pick something. Like over here, I love to use 0. If I can use 0, it just is so easy because you just put in 0 squared minus 8 times 0 plus 12. So that would give me 12. Is 12 less than 0? No. So that's a frowny face. Okay, so something between 2 and 6. How about 4? So I'm going to say 4 squared minus 8 times 4 plus 12. So that's negative 16 plus 12. That's negative 4. Is that less than 0? Yes. Happy face. Okay, and then something bigger than 6, so 10. So I'm going to have 100 minus 80 plus 12. That's 20 plus 12 is 32. Is that less than 0? No. Okay, so where are my solutions? My solutions are between. And so the way I'm going to write that is I'm going to write x such that. I find it really helpful, like if you're wanting to write it, you have to be able to write it in number line order. Okay, that x has to fit in between. And you were never going to write it something like this. It is incorrect to write it like this because that's not number line order. And you're saying x is greater than 2, less than 6, but it's like writing an interval backwards. You can't do that. And so if you see something like that, then that is wrong. So we're going to write x is between 6 and 2, and it's less than, not greater than or equal to, or less than or equal to. And that's your solution, or those are your solutions. So anything in between. Okay, on number 8, when you got everything to the one side, you went to try to factor it probably, and you find out it's not factorable. So we have to use another way to solve. So I'm going to use the quadratic formula. So negative 2 plus or minus the square root of 2 squared minus 4 times 1 times c times 2, or over 2. So negative 2 plus or minus 4 minus 20, and we see where this is going. So that's going to be negative 2 plus or minus an imaginary number. So it's 4i over 2. You can't put that right there. And so that makes us wonder, okay, so what do we say? Do we say no solution? Go back and look at the original problem. Okay, it's saying that any number squared, which will be a positive number, plus 2 times the number, plus 3 is going to be greater than a negative 2. So really what we need to do is we need to just check some numbers. Okay, let's try something negative 100. So negative 100 squared is going to be positive 10,000, and 2 times negative 100 plus 3, is that greater than negative 2? That is. So let's try something in the middle of the road, like 0. 0 squared plus 2 times 0, 3. Is 3 greater than negative 2? That is. Let's try something on the other extreme. So like 100. So 100 squared is 10,000 plus 2 times 100 plus 3. Is that greater than negative 2? So you can see from that one that anything positive is going to make that a true statement. And we saw that when we have negative numbers, like that's true. Let's try something like negative 1. Negative 1 squared plus 2 times negative 1. So that's going to plus 3. So we're going to have 1 plus 2 times negative 1 plus 3. That's going to give me negative 1 plus 3 is still 2. So that's going to come out to be positive. So I'm pretty comfortable in saying this is always going to be true. So we're going to say x such that x is an element of the real numbers, or you could say an interval if you wanted to, but it did say set notation, so I'm going to write that. So when you have, when you solve it and you get like imaginary numbers, you have to go back and check and see like, is that always going to be true or not? So is this part always greater than negative 2? Okay, we're going to continue the rest of this lesson in the next video.